So today I'm going to talk about the Big Bang, and specifically my title is 14 billion years in 90 seconds. Now what I'd said in the email was Big Bang in 30 seconds, but that may have been a little ambitious and I just forgot what I called it before. But my point is not that I can tell you the Big Bang and explain all of physics in 90 seconds. My point is that we should generally try and arrange our thoughts and arrange our evidence in such a way that if we are brought into an elevator and someone looks at us and says, well, I heard that the sun is shrinking by a certain amount, therefore, if the universe was 14 billion years old, the Earth would have been inside the sun only a few billion years ago, therefore evolution's false, because the universe can't be that old. And this argument may sound facetious and absurd, but I was told to it by a creationist once, and it just stood out to me because I was so baffled by this argument that I needed some kind of response. And so I had to look into it, I had to say I needed to see the papers. But the point is you want to be able to compress your thoughts so that if you walk into that elevator, you can talk to this person and get a clear picture of why we believe in the Big Bang in a way that's accessible. So the Big Bang Theory is not the TV show. It's I had a picture of the TV show and then like an X comes up, but my jokes are all in my slides because I'm not that funny. The Big Bang Theory is the unifying theory of everything. It sort of explains why there is something rather than nothing. It's why the universe is here. The basic idea is the universe is big now, but it was much smaller in the past. Therefore, at some point in the past, it was a very tiny point. It was smaller than the point of that laser on the wall, smaller than the head of a pin. Everything was in there. And then within seconds, it had expanded through something called inflation that physicists don't really understand. They just use it as a filler to say we got from that point to much bigger, and then eventually stars, galaxies, planets formed, and then eventually we got here. So Big Bang Theory accounts for all of this and all of our known observations. And the key point that I want to emphasize multiple times is that, like evolution is to biology, Big Bang Theory is consistent with everything in physics that we know. Every observation we have generally confirms it. So I want to talk about 5 major arguments for the Big Bang Theory today. I want to talk about the redshift of stars, the abundance of the elements in the universe, the cosmic microwave background radiation, how the age of stars, the observational age of the oldest stars, and how galaxies evolve. And these are the 5, I think, most convincing arguments and evidence for the Big Bang. So the first one is the redshift of stars. Now we all know the Doppler effect. This is when a car or a train goes by you and it makes that eew sound as it comes from a really high pitch as it's approaching you, and it goes to a low pitch as it moves away. So that has to do with as an object is approaching you, the sound waves get compressed, so they sound higher in frequency. And as it goes away from you, the sound waves are stretched out as it moves away, so the sound gets lower. Now the exact same thing happens with light. As an object is moving towards us, the light gets actually higher in frequency, so it gets more blue. And as something is moving away from us, it gets more red. Generally, we can't see that. You know, as a car drives towards you and away from you, it doesn't change colors because it's not going fast enough. But if we look out at stars, we can actually map what colors they are, generally compared to what we expect. And we notice that every star in the galaxy is redder than it should be. And stars that are farther away are even more red. So the question here, or the observation here, is that the universe is expanding. If everything everywhere is moving away from us, though, I think that poses a couple key questions. First, how do we know how far stars are away? When we look up, all stars look like they're just sort of against the sky, and just looking at them, it's hard to tell any depth. And the second question is, if everything is moving away from us and the stuff moving away farther is moving faster, doesn't that make us the center of the universe, and doesn't that make Galileo wrong? So to address the first question, we have a very good idea of what stars are. There are a few key classes of stars, and stars generally produce a fingerprint. They have a certain spectrum of light. And so we can look at a star and look at the fingerprint of light that comes off it, and that allows us to say, all right, this is a class M star. And then we can compare what we know about that kind of star to how bright it should be. And if a star is very dim, that means it's very far. Just like if you took two light bulbs and you put one on the far side of the room and one right up next to you, and you knew they're both 60-watt light bulbs, you could just tell by how bright that farther bulb is compared to the close one to know how far it is. And that's how we tell how far stars are, generally. We have other methods, and we also use supernovas in the galaxy for things that are even farther than stars. But that's the basic idea. The second question, are we the center of the universe, is a little trickier to think about. And the best analogy I can think is if you take a balloon and put a bunch of dots on it, and you blow up the balloon. As you blow it up, this is space expanding, and space is expanding everywhere. So every dot is moving away from every other dot. If you pick a dot on there, it looks like the closest dots are moving away the slowest, but the farther away dots are moving faster. If you then shift your perspective to a different dot, it looks like everything's moving away from that dot on the balloon. So as the universe expands everywhere, it looks like everything is moving away from everything else. So it's a little conceptually difficult, but maybe you can convince yourself. I had some graphics with some dots and arrows, and they shift. I was proud of it when I made it, but it's not that important. So that's the first argument, is the redshift of stars. So we see everything's moving away. That generally means everything was closer together in the past. This contradicts the alternative theory of the steady-state universe that had been around forever, because if everything was closer, everything would have been hotter, and it just doesn't work that everything can be expanding away from each other forever. The second argument is the abundance of elements. So if we look around the universe, we see different elements, and we see hydrogen, helium, oxygen, carbon, and all the higher elements. But what we notice is that 75% of those elements are hydrogen, and then another like 20% are helium, and then a tiny sliver is oxygen, and then about 1% of what is left is all the other elements, like lithium and carbon and nitrogen. Everything is basically a little bit. And the key idea here is how the Big Bang accounts for the elements. So what happened in the Big Bang is right at the start, the universe was so hot that nothing could really exist as we know it today. Everything was so hot and dense. As the universe started to cool, elements started to form. Elementary particles formed, and then those formed hydrogen. And then some of those combined to form helium. But generally you could only get helium and maybe lithium, the third element, through the Big Bang. After that, the universe just got too cool and too far apart for any higher elements to form. So if the Big Bang is correct, there should be a lot of hydrogen and a lot of helium because they formed very early. But where did everything else come from? Well, as Carl Sagan told us, we are star stuff. And so what happened after the Big Bang is hydrogen and helium started to come together, and gravity slowly pulled stars together over millions of years. And eventually these stars got so dense and the gravity was so strong that they started fusion. And so you had hydrogen fusion, and that would form helium. And then you would get helium and hydrogen fusing together to get oxygen. And then you'd get even more dense stars. And then when these stars explode in supernova, that pressure and that force creates all the other elements. So it takes supernovas to actually give us all of the elements that make up life. Without, stars dying, we wouldn't be here today, which is a pretty cool thought, I think, on its own, let alone the fact that this proves the Big Bang. The alternative theory is the steady-state universe, that we've been around forever. And in that kind of picture, supernovas would have been going off for all of history, and therefore we would have had a much more even distribution of elements. We would have had a lot more of the heavier elements, but this isn't what we see. The next argument is potentially the one that convinced most physicists, and it wasn't actually discovered until 1968. So until the 60s, physicists still didn't really know why the universe was here. Some said it was around forever, like Fred Hoyle. Others had started to propose the Big Bang since Einstein's general relativity had a solution there. So what the cosmic microwave background is just this uniform radiation cloud almost surrounding the universe. And if we look out really, really far as we can, so we take Hubble and we extend that, and so we look as far as we can, it turns out there's this glowing background that's almost perfectly uniform. And so how the Big Bang accounts for this sort of shield is that when the universe was really dense, it was so hot that light couldn't even escape. When you have something like a plasma, which is what a really hot, dense combination of matter is, light can't get through it, it just gets absorbed all over. But as the universe cooled, light finally escaped. And so when that light escaped, that made this background. And so it started really hot because it was really small. But as the universe expanded to our current size, it cooled off. Because you take the same amount of heat and spread it out, it gets colder. So right now we have about a uniform 2 Kelvin or 3 Kelvin shield around the universe, which is perfectly consistent with the age of the universe. Which is really cool. And how they discovered this is also a great story of these physicists and engineers for Bell Labs. They were trying to do radio telescopes, and they were trying to look out into the stars to see whatever they could see. But they noticed there was this interference and this noise on their telescopes. And so they went in, looked at the telescopes, and they noticed some like seagulls had set up nests on them. So they cleaned away the seagulls, and they just cleaned the poop off the telescopes. And they still found this noise. And they went step by step, and they questioned themselves like any good scientist should. And they found there's still this noise. So they published this result and said, look, something's noisy out there. Why is the universe noisy? And then someone else who was pretty smart said, well, I guess that's because the Big Bang is right. And then physicists went, all right. And we can extend this a little bit further. And as they looked at it, it turns out this shield isn't perfectly uniform. There's very slight variations. And this is important because if the universe was perfectly uniform at the Big Bang, why would there be something? Why wouldn't it just stay uniform and sort of stay boring? And it turns out these little bumps at the initial, little random bumps at the initial Big Bang are what allowed gravity to take hold in different spots and form galaxies and stars. So without little bumps in the universe, little random noisy bumps, there would be no life. So physics gives us all kinds of things. And they have models that show, that sort of plot the amount of these bumps, and they fit the data perfectly, like to almost incredible precision. My next argument is the age of stars. So one way to prove or to verify a hypothesis is to propose a counter example, like if the universe is 13.7 billion years, then we should not see any stars older than that. And so we can look around and we can use our models of stars and look at the farthest galaxies and ask how old are these stars. And the best estimates we have are all, the oldest stars we can find are all around 12 to 13 billion years, plus or minus 1 or 2. So the error bars are pretty big because the models for star formations are pretty bad. But even the oldest star isn't proposed to be older than the universe within its error. So every star we look at fits within the Big Bang model. Compare this to the idea of a steady state universe. We should be able to look out and see a 16 billion year old star and say, well, that's unusual. And if we saw a 20 billion year old star, we go, well, that doesn't work. Where did that come from? That couldn't be here. But we don't. So it doesn't prove the Big Bang, but it verifies it, which is important. My final argument is the evolution of galaxies. And so within the Big Bang model, it proposes that early galaxies should be very far away from us because they would have been formed very early and been moving away from us since the Big Bang. And they should look very young. They should be very rich in hydrogen and not many of the higher elements. And so as we look with the Hubble telescope and these other big telescopes in space, we see old galaxies near us, and we see very young galaxies very far away. And it just fits very beautifully with the theory that young galaxies are near the Big Bang, and as we come towards us, we're more in time. And you have to remember, when you look into space, you're looking into the past, just because light takes so long to travel. So the 5 arguments I went through were the redshift of stars, the abundance of the elements, the cosmic microwave background, the age of the stars, and the evolution of galaxies. And there are other arguments, and I took all of these from the Top Origins archives, which I'll email out in I'll email it to Nancy so she can put it in the newsletter. And that's basically what I had today to talk about. I have lots more that I can, and we have 1 or 2 other physicists in the audience who can maybe help fill in any questions, but